The colossal impact is an idea that has outlined how we could unravel the universe, illustrating the supporting of ebb and flow cosmology, as per Einstein's theory, furthermore known as coarse-perusing cosmology. The monstrous impact was the second the universe began its advancement, demonstrating the development of all matter, energy, and presence. This event happened commonly 13.8 billion years ago and provoked the titanic universe we notice today. However, late enhancements in cosmology propose the monster impact undoubtedly wasn't unquestionably the start. Rather, there could have been a phase before the monstrous blast that was equivalently basic in embellishing the universe. Taking everything into account, this pre-period is known as boundless development. Improvement is potentially one of the most fascinating bits of present-day cosmology. It suggests that before the hot, thick season of the colossal impact, the universe went through an extraordinarily speedy close to emotional advancement. During this period, the universe was expanding in size at a stunning rate. To definitively address how silly this augmentation was, if the universe started more unassuming than an iota, it would have reached out to be unfathomably greater than the whole recognizable universe within a microscopic piece of a second, around 1/4,000,000th of a second. This expansion stage didn't last long, but it played a critical role in shaping the universe. When the inflationary stage finished, the energy driving this augmentation was released into space, warming it up and making the particles of matter that make up all that we find in the universe. In various ways, advancement is the herald to what we consider the huge impact. While the theory of expansion is by and large accepted in cosmology today, various unanswered inquiries remain. For example, we don't yet comprehend which started development, what compelled it to stop, or how long it got through. These are open questions in cosmology, and taking note of them is huge for a more profound understanding of the beginning stages of the universe. Before improvement, the universe was a remarkably thick little spot of issue, frequently alluded to as a quirk. From this eccentricity, advancement began and eventually led to the formation of molecules, particles, stars, and galaxies. The chance of the epic impact as the beginning of everything is captivating. However, present-day cosmology suggests a more complicated picture. Some theories suggest that the universe went through a stage before the monstrous impact. During this stage, inflation caused the universe to expand at a staggering rate, growing in size by a factor of 1,000,000,000,000 in a negligible portion of a second. This rapid expansion was fueled by an odd construction of energy that entered void space. Right when expansion finished, the energy that had driven this development was transformed into particles, warming the universe and inciting the hot, thick state we call the enormous impact. This inflationary stage was cold and void, but it set up for the development of matter and the universe we see today. One of the more hypothetical contemplations in present-day cosmology is the possibility of immortal extension. This theory suggests that extension didn't shut down simultaneously. Rather, it ended in patches, making many pockets, each of which could be a universe by its own doing. Our universe would be only one of these patches. According to never-ending extension, there could be an infinite number of these universes, each with its own set of physical rules and constants. This is where the chance of the multiverse becomes a necessary element, that our universe may be one of many or even an infinite number of universes. If this idea turns out to be true, it would explain why our universe is so finely tuned for life. In this multiverse situation, each possible combination of physical laws could exist in different universes, and we end up residing in one where conditions are ideal for stars to form and for carbon, oxygen, and various elements crucial for life to exist. While theories like immortal extension and the multiverse remain speculative, the chance of inflation itself is grounded in observational evidence. The strongest support for inflation comes from the cosmic microwave background radiation, CMB, the oldest light known to man. The CMB was emitted around 380,000 years after the Big Bang, when the universe cooled enough for particles to form. By then, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a baby picture of the universe. The light provides clues about the universe's earliest days, helping scientists understand what happened shortly after the Big Bang and offering support for the inflationary model. One of the main discoveries came from the European Space Agency's Planck satellite, which took detailed pictures of the CMB. These pictures reveal slight variations in the temperature of the early universe, and these variations match the predictions made by inflationary theory. This preliminary evidence strengthens the idea that inflation isn't just a theoretical hypothesis, but a critical part of how we understand the universe's origins. Sorting out the Big Bang and what went before it requires combining two of the principal theories in modern physics: Einstein's theory of general relativity and quantum theory. General relativity describes the large-scale structure of the universe, including the behavior of galaxies, stars, and planets, while quantum theory describes the behavior of particles on the smallest scales. To answer the major questions in cosmology, such as what lies beneath the surface of the universe and where it came from, scientists must develop a theory that combines these two systems. This would allow us to understand the Big Bang, as well as the conditions that led to it. One of the most stunning pieces of the universe is its size. The most distant objects we can see are around 47 billion light-years away, meaning the observable universe is around 94 billion light-years across. This might seem unusual, given that the universe is only 13.8 billion years old. How can the observable universe be greater than the time it would take light to cross it in the age of the universe? The answer lies in the fact that the universe has been expanding over time. As the universe grows, the distance between objects increases, making distant objects farther away than the time it would take light to reach us. Most scientists agree that the universe extends far beyond the observable universe. In fact, it's possible that the entire universe is infinite in size. The observable universe is essentially the part we can see, limited by how long light has had to travel since the Big Bang. There may be vast regions of the universe that we will never be able to see. While it's possible the universe is infinite, the question remains: is there anything beyond the universe? Most scientists are skeptical of this idea. If the universe is endless, there is no outside to it. The universe would simply continue indefinitely. Whether or not the universe is finite, it likely won't make sense to talk about anything beyond it. Beyond would imply something outside space, which itself is a property of the universe. So, the idea of something beyond the universe may not have any physical meaning. Just as the origin of the universe is a subject of immense study, so too is its inevitable end. The most current measure is that the universe will continue to expand forever. This is attributed to a mysterious characteristic known as dark energy, which is causing the universe's expansion to accelerate. Before the discovery of dark energy, scientists thought the universe's expansion would eventually slow down due to the gravitational pull of matter. There was even a possibility that the universe could stop expanding and begin contracting, leading to a big crunch. However, dark energy appears to be pushing the universe apart at an ever-increasing rate. If this acceleration continues, the universe will keep expanding indefinitely, eventually reaching a state where galaxies are so far apart that they become isolated from each other. In this scenario, the universe would become cold, dark, and devoid of energy. Stars would burn out, galaxies would drift apart, and matter would eventually disintegrate. This is sometimes referred to as the Big Freeze or the heat death of the universe. The story of the universe, from the Big Bang to its possible end, is one of the most important and complex tales in science. While we've learned a great deal about the universe's origins through the theory of inflation and the study of the cosmic microwave background, many questions remain unanswered. What started and ended inflation? What lies beyond the observable universe? Is there a multiverse, and if so, how many other universes exist? As scientists continue to study the universe using advanced technology and theories that combine quantum mechanics with general relativity, we will undoubtedly gain further insights into these mysteries. The journey to understand the universe is ongoing, and each discovery brings us a little closer to answering the profound questions about our reality. The study of the universe's origins and structure is not just a scientific endeavor. It also raises philosophical questions about existence, reality, and our place in the universe. One key area of interest in cosmology is the concept of dark matter, which is believed to make up roughly 27% of the universe's mass energy content. Unlike ordinary matter, dark matter doesn't radiate or interact with electromagnetic forces, making it invisible to current instruments. Dark matter's existence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. Although it has never been directly detected, its influence on the structure and behavior of the universe suggests it plays a crucial role in shaping cosmic evolution. Without dark matter, the gravitational pull between galaxies would be too weak to account for the structure we observe in the universe, such as the way galaxies cluster together. Its presence is vital in holding galaxies, galaxy clusters, and even the universe itself together. Another area of focus is dark energy, which is believed to make up about 68% of the universe's energy content. Unlike dark matter, which exerts gravitational pull, dark energy seems to have the opposite effect. It causes the expansion of the universe to accelerate. While we know dark energy is a dominant force in the universe's expansion, scientists are still puzzled about its true nature. The discovery of dark energy was one of the most significant breakthroughs in modern cosmology. It was first observed in the late 1990s when astronomers found that the universe's expansion was speeding up rather than slowing down as previously expected. Together, dark matter and dark energy make up about 95% of the universe's total mass energy content, leaving only about 5% to consist of ordinary matter, everything we can see and touch. This vast, unknown portion of the universe remains one of the greatest mysteries in physics and cosmology. As technology advances and new observational techniques are developed, scientists hope to unlock the secrets of these mysterious components and their role in the universe's fate. The future of cosmology may also depend on the development of a theory of everything, a unified theory that can reconcile the two pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics describes the behavior of particles at the smallest scales, while general relativity deals with the forces at play on large scales, like gravity and the motion of planets and galaxies. These two theories have been extraordinarily successful in their respective domains, but they are incompatible when it comes to extreme conditions, such as those present at the very beginning of the universe or inside black holes. A unified theory could provide a deeper understanding of the Big Bang, the behavior of black holes, and other cosmic phenomena. Cosmology is not only about looking outward into the universe, but also inward, toward the fundamental laws that govern reality. Theoretical physicists are working on ideas like string theory and loop quantum gravity to bridge the gap between quantum mechanics and general relativity. String theory, for example, proposes that the basic building blocks of the universe are not particles but tiny, vibrating strings of energy. These strings could explain the fundamental forces of nature and potentially lead to a better understanding of the universe's origins and its ultimate fate. Despite the progress made in understanding the universe, there are still countless unanswered questions. Why does the universe have such an astonishingly precise set of physical constants that allow life to exist? Is our universe part of a multiverse, a vast collection of separate universes, each with its own set of physical laws? Could there be intelligent life elsewhere in the cosmos, or are we alone in the vast expanse of the universe? As our understanding deepens, we may be able to answer some of these questions, but many others may remain beyond our reach. The study of cosmology offers a unique window into the nature of reality itself. It challenges our understanding of space, time, and existence, and forces us to confront questions that are both profound and humbling. Whether we are peering into the depths of space, investigating the origins of the universe, or speculating on its future, the search for knowledge in cosmology is a journey that will continue for generations to come. As humanity explores the cosmos, we not only seek to understand the universe, but we also explore our place within it. The study of cosmology invites us to consider the broader meaning of existence, prompting us to ask, what is the purpose of the universe? Are we alone in the cosmos? What happens when the universe reaches the end of its life? In the coming years, technological advancements will continue to provide more detailed and accurate observations of the universe, helping us answer these profound questions. Whether it's the construction of new space telescopes, the development of particle accelerators, or advancements in computer simulations, each breakthrough brings us closer to unlocking the secrets of the universe. Through this exploration, we can continue to expand our